This video explains the photoelectric experiment. Right, so we're trying to develop a historical perspective on quantum mechanics. The first experiment that we have talked about is the black body radiation experiment, in which the idea is that if you have a body at a given temperature, this body gets rid of energy by emitting electromagnetic radiation, like visible light or infrared light, with energies that are in very specific amounts, which are called quanta. So if you emit some energy at a particular frequency, whatever this is now, that energy, that the emission can only be in discrete amounts of these very well-defined energy. So this is what we call quanta or discrete packets of energy. So with this idea, then Einstein proceeded to explain something that is called the photoelectric experiment. Alright, so what is the photoelectric experiment? The experiment is fairly simple. You have a metal surface. This could be any metal that you want, for example, copper. And the idea is that you're going to shine electromagnetic radiation. Typically, this is going to be in the ultraviolet. And when you shine that electromagnetic radiation to this metal surface, what happens is that electrons get ejected. Now, and there are some key characteristics of this experiment that were unexplained by classical theory. So this is the kinetic energy of the ejected electron, as a function of the energy of the radiation that you're putting in right here. So it turns out that until you have a minimum amount of energy, no electrons get ejected. But as you start to increase the energy of this electromagnetic radiation that comes to the metal, then electrons might get ejected. But something interesting that happens is that the kinetic energy of electron increases linearly with the energy of the electromagnetic radiation that you have put in. So this is something that was not able to be explained by classical theory. And Einstein provided a solution to this. The idea of Einstein is as follows. Look. Planck has said that when you actually have a hot body, the way that to get rid of energy is by emitting electromagnetic radiation in very discrete amounts that have values of h nu or integer values of h nu. Maybe the reason is that every type of electromagnetic radiation, regardless of whether it comes from a hot body or from any other source, actually travels in these discrete amounts, which are called quanta or h nu. Another thing that happens then is that these traveling packets of energy actually have particle properties, and this is kind of a big concept. Notice that, again, this electromagnetic radiation does not have any mass. When you think about visible photons, they do not have any mass. Yet, this experiment can be explained if you assume that even if those packets of energy don't have any mass, they have some particle properties. And particles are objects that have mass. And the particle properties are that these light particles that we call now photons, can actually collide with electrons on the metal surface and then eject them. So if that's the case, then we can actually explain this experiment. Alright, again, now this is a photon that has a very well-defined energy, and even though it does not have a mass, it has some particle properties like being able to collide with other particles. Right? So this photon arrives at the surface, and if the energy with which it collides with the metal surface is not large enough, then it's not going to be able to dislodge an electron. But if the energy is large enough, then a collision will take place, and then you will be able to kick out the electron. Now the more violent the collision, the larger the kinetic energy of the dislodged electron will be. Right? So if you hit the surface with a photon that has very high energy, then the excess energy is going to be carried out by the electron in terms of kinetic energy. There were a couple of aspects of this experiment that were not very well explained as well. So for example, an idea was to say, well, maybe I can increase the kinetic energy of this electron, how fast the electron moves, if I come in with a very intense source of light. Okay, so instead of sending 10 photons at a particular frequency, I'm going to send 1,000 photons at a particular frequency. Now, the total energy that I'm putting in the surface is very high, so I'm expecting those electrons to be ejected at really high velocities. But that is actually not what you find. You find that when you send 10 photons, you might eject 10 electrons at a given kinetic energy, but if you send 1,000 photons, you don't eject 10 electrons at higher energy. You might be able to eject more electrons, but at the same energy as what you had with the 10 photons, right? And again, the idea is that there is a correspondence between the photon energy and the energy of the ejected electron. Again, that can be explained if you assume that each photon is going to cause a collision with an electron, and then the electron gets ejected. Okay? So anyway, so all of this can actually be put into a very simple expression, which is what we call the photoelectric effect equation. All right? So the energy that you put in, okay, is the energy of this photon, has to be identical to the energy that you get at the end. Okay, so that is fairly simple. All right, what is the energy you actually get initially? The energy of one of these photons, one of these particles, is h nu, which is what Planck had said. If you have 2 photons, then the energy will be 2h nu. All right, so that also gives you a sense of what the quantization of the energy is. Right, the energy of that source can be a number in between h nu and 2h nu. If you have 1 photon, it will be h nu. If you have 2 photons, it will be 2h nu, but it will never be in between. Okay? That energy of the photon is invested in 2 different cases. The first thing you have to do is to actually break off the attraction of the electron with the metal surface, and that's something that depends on the metal. That's something that we call the work function of the metal, and it has the Greek letter, or we denote it with the Greek letter phi. Okay, that's what we call the work function of the metal. And again, this is simply the amount of energy that it takes to break the electrostatic attraction of that electron with the nuclei of that metal surface. If you have more energy than what it takes to just break up the interaction, then the rest of the energy will be invested in accelerating the electron to a given velocity. Okay, so this is going to be equal to the kinetic energy of the electron, and now the electron has a mass, albeit small. Okay, so this is going to be equal to 1/2 mv squared. We know that that is the kinetic energy of a regular particle that has a mass. Again, this is the photoelectric experiment, and this is revolutionary for various reasons. For one, it validates Planck's idea that electromagnetic radiation has this value for the energy. Okay? Now, the second thing that is very revolutionary is the idea that all electromagnetic radiation, UV, vis, X-ray, infrared, radio frequency, okay, all of those are something that we call light particles or photons. And the idea is that even if that electromagnetic radiation does not have any mass, it has some particle properties, as if it had a mass. Right? So the idea is that you can send this massless radiation to a surface, and then you can actually eject, as if you had a collision, okay, an electron, which is a regular particle, right? Has a mass, has a velocity, and so forth. Okay, and the way to actually connect that is with this very simple expression with which you can do some homework problems.